Starting to record. All right. All right. So for the first time, I got everything set up, okay, except for the screen share on this device. So let me get that set up too. Entering, it's connecting to Wi-Fi. So for some strange reason, in this room, this tablet is having problem connecting to the Wi-Fi. So that part is really puzzling. Okay, go to Wi-Fi. And it doesn't see the 5G network from my router from here, but it would see a bunch of other networks, but only in this room. So this is a really strange thing. So let me reboot my tablet and see if that will fix the problem. All right. So starting today, we are starting with a new topic, unless there are questions about relations. So we all good on relations, okay, including the homework assignment. No questions about the homework. You want to talk about the homework? The G function? Oh, did we not finish the? Okay, maybe we forgot, right? I forgot to finish the G function. No, we actually did finish the G function question. Are you talking about the practice exam? Okay, so let's see. I think I already have it downloaded here. There we go. Okay. All right. So I think it's this one. Yep. All right. So the G function question is this one. And all right, so I think we did talk about this one in class. So do you have a specific question about it? All right. All right. So the first thing is, where do we find the G function? I suppose, that would be a good starting point. So the G function is also known as, I just call it the G function, but it's also, more formally known as Cantor's pairing function. And we talk about that in the Aleph Null module. So this is where we talked about it. And then we go to this one here. So this is where we talk about the G function. And this is the derivation. And then we go straight to the actual definition of the G function, which is right here. So if you go here, that's the actual function definition of G itself. Basically, you give it a two tuple, which is made out of two natural numbers, and it'll give you a single natural number back, which is essentially the label that we put on the tile. Okay, so that's the G function. The G function has an inverse function because it is a injective and surjective function. So that's why it's also bijective. And any function that is bijective has an inverse function. So the inverse function is derived, keep going, right? Keep going. This is the inverse function. So the inverse function, which is noted as g and then -1, because that's how we denote a inverse function. So if you give it a natural number n, then we can use xn, yn as two other functions to give you the x coordinate and also the y coordinate. The xn or x as a function looks like this. Okay, so the final form of the xn is like this. It's wn minus n plus this mess over here, and then the yn is here. So those are the two x and y functions based on n. So when you put those two into a two tuple, then you actually get the coordinate back. So for people who don't want extra complication, you can always refer to Wn. So Wn times Wn plus 3, the whole thing divided by 2, and then that whole thing minus n is the x coordinate. and then n minus wn times wn plus 1, and then the whole thing divided by 2 is the y coordinate. So you just give it the n, which is a natural number. It will give you back the coordinate of the tile that is supposed to get that particular natural number. So that's kind of the most important part of this module, when it comes to Cantor's pairing function, is the pairing function itself and the inverse of that. So most of the other part of this entire module is the derivation of how do we get to the function itself in a closed form, and how do we get to the inverse function also more or less in a closed form. W of n is really just one of the roots of the quadratic equation. So yeah, we are just picking one of them, and then we also use a floor function here to make sure that we only use so that it becomes a natural number to guarantee the inequality in the derivation. So this is the earlier derivation here. It was an inequality, so we just want to make sure that it is all leaning in that direction, and that's why we need a floor function. All right. So is that helping? Okay. All right. And then the other thing that is also important about Cantor's pairing function is it is really just based on how we fill the tiles in a two-dimensional space using the diagonal approach. So that is really important. Except in the notes, I do not have a picture of how that works. I only have a pattern of how the tiles are labeled by natural numbers. But if you make your own grid, okay, and fill in the tiles with these numbers, then you will start to see the pattern. All right. So are we good with that? Okay. All right, cool. So now I'm going to give this a try again. First of all, I need to make sure that I'm connecting to the right Wi-Fi. And let's see whether it works or not. Nope, it is still not working. Something about this room is really weird because I don't have this problem when I was in 306 or 305, but somehow in this room the tablet cannot see the router, but the PC has no problem seeing the router. So it is a very interesting, unique problem. That's one way to put it. So, hmm, all right. Well, I guess that is not going to work today. If it's not going to work, it's not going to work. So what we'll do, we have the recorder already started. So what we'll do today is, let me get my cursor back up here. So we are now going to move into propositional logic, okay? And today is the first day. We'll probably spend maybe 2 or 3 days to talk about this. This is a longer module. And the overview is, okay, what exactly is propositional logic? I mean, you don't need me to tell you what is propositional logic. You can ask Google, you can ask ChatGPT, you can ask Gemini. There are many, many sources where they will explain to you exactly what propositional logic is. Propositional logic is basically a very formalized system to argue in logic. All right. So you might ask, so exactly what are you talking about, right? So I can give you an example. Okay. So let's just say that, mm, okay, people feel refreshed after they sleep in a class. Okay, so that's a statement. Okay, we'll assume that statement is actually true. Okay, so people feel refreshed after they fall asleep in a class. um, I'm trying to make sure that I have the logic right. Okay, um, okay, and then we say, I see some of you coming from Iraj class earlier look really refreshed. Okay, so now the question is, can I say that you actually fall asleep in Iraj's class? Is it is it a fact that I can deduce that you fell asleep in Iraj's class, or is it really just like, well, that's one of the reasons why you look refreshed? It's only one of the reasons why you look refreshed. I cannot prove that you actually fell asleep in Raj's class. Okay. So it's only when I use the term only if, okay, then I can prove that, okay, because the word if versus the phrase only if, they mean different things. Okay. So it's kind of like that, So back in, I guess, the Greek days, the wise people, they like to argue with each other. So they would derive, this entire whole system to make sure that, the logic itself is correct when they argue with each other. And if you don't believe me, you can go to Wikipedia or do a quick search on propositional logic. And Wikipedia, okay, it's a fundamental branch of formal logic that studies how propositions, statements that are either true or false, are combined and modified using logical connectives to form more complex sentences. So note statements and how these combinations affect their overall truth value. So to us, okay, this is not exactly how we are going to do it. So I will give you an example of what it looks like, what people use, and why it is not something that is of interest to me. And as a result, I don't focus on that particular side of propositional logic a whole lot in this class. All right, so there are a few things, okay, I can give you an idea of what people do, okay? And since my tablet, for some really odd reason, just doesn't want to work in this room. My tablet is cannot see the 5G, or not the 5G, the 5 gigahertz version of the router. It can see the other one, but I don't really have the password to sign in, so I'm gonna have to use my mouse pad to do the explanation. There we go. All right. So we're gonna work with something like this. So if I say P and Q. I'm using C++ syntax here. So if I say P and Q is true, okay, what do I know about P and what do I know about Q? What can this imply? What can I deduce from this statement? Both of them must be true individually. So I can now say P has to be true and Q also has to be true. So I have just applied one of the many rules in propositional logic, and there's a whole bunch of these things. Okay. So another one that is really kind of famous, people use it a lot, is to say, P implies Q. So if we know this statement is true, and we also know, P is true, oops, P is true, then what can we say about um, this whole thing? Can we come to any type of deduction? So Q is also true in this case. That is correct. Now we can also flip the whole thing, okay? We can flip the whole thing and we can say P implies Q is true. In other words, the implication itself is a true statement. But this time we say, oh, we know Q is false. Or we know, let me see, let me think about this. We can say that Q is, I don't think we can come to that conclusion. Okay, I have to, let me, give me a second. I have to think about this a little bit. So if we know that Q is false, yeah, yep, this is what we do. So if we know that P implies Q is true, we know that Q is false, can I come to some kind of conclusion about P? P has to be false. That is correct. So P also has to be false. So now you're looking at three different examples of what we call propositional logic. So each one is what we call a production. Okay, so I'll explain that using the proper terminology or symbols, when we get down to the notes. So you can see this is really kind of mechanical, okay? It's pattern matching, okay? If you find this to be true, if you find this also to be true or false, whatever, the pattern is, then you can also say, okay, this also has to be true or, has to be false, okay? So that's basically propositional logic, and it's really kind of complicated in the sense that there are many rules involved. So if I were to look up, propositional logic, say in Wikipedia, okay, so let's go to Wikipedia. There we go. It will give you a laundry list of the connectives, or what we call connectives. These are just the operators. But if you look at the rules, okay, so let's skip all the way to the rules. Oh, come on. There we go. There we go. No, no, these are not the rules yet. So let's move on. Okay, so these are some of the rules, and this is a good table right there. Okay, this is a good table. So in this notation, which is also kind of what we are using in our class, except we're going to use a slight variation of this. It is basically saying P implies Q. So, in Wikipedia's notation, this is implication. It's the same thing as the double bar right arrow that we use in this class. So this is basically saying P implies Q being true, and P being true, this is called infers. Okay, it infers Q is true. If P implies Q is true and not Q is known to be true, which is basically saying Q is false, that infers that infers not P is true, but if not P is true, it's the same thing as saying P is false. So that's basically the same thing that we just talked about, right? So each one of these has a Greek name, okay, or some of these have a Greek name, and then you have to memorize what it looks like, okay, and then you have to learn how to apply that, okay, and it's long, okay. The list is rather long in this case. It goes like it keeps going and going and going and going. Okay, so that means, but the whole idea is using these, what we some people call these productions, and some other people call these inference. So basically, what we're doing here is, if I just give you a bunch of statements, okay, using and or not, implication, equivalence, and so on, and I say, okay, don't ask me why, but this collection of statements, they are all true, okay. And then I go to one particular expression and I ask, what about that one? Can you show me whether that is also true, you know, as a result of these initial ones being true? That is derivation. Okay, I need to derive or deduce, whether a particular statement is true based on an initial set of statements known to be true. So that's the whole premise of propositional logic. So are we getting an idea of what it is used for? Okay. Yes. Okay. All right. So now we're going to shift our focus just a little bit to a general idea of, okay, but what is a proof? Okay. When you're taking a math class, it doesn't even matter which math class we're talking about. It can be calculus, can be linear algebra, can be just regular algebra and whatnot. What exactly is a proof in a math class? This classroom somehow always does not have dry board markers. Okay, that's okay. I don't really need to convey the picture, but what exactly is a proof in a math class? Yes. Okay, so the result is essentially a statement that can be true or false. But most of the time, your professor wants you to prove a statement that is true, right? So basically, your professor says, okay, we know this conclusion is true. We also know that we start with these premises. Okay, so in an algebra class, we start with the commutative law, we start with the distributive law, and so on and so forth. And then they want you to establish a link or a chain of implications. Okay, and every implication is saying, okay, if I know this and this, then this has to be true. If I know this and this has to be true. So now you have not really exactly a chain, but a mesh of these implications. And the idea is I need to connect all of these all the way to the one statement that you were asked to prove. Okay, so that's basically what a proof is. So are we good so far in terms of just understanding what a proof is in general in mathematics? All right, cool. So now the question is, Do we can we make a computer do all the proofs for us? So why do we want to do something like that? Well, because I don't want to waste my time in my calculus class and I just want to use a machine to do it for me. Well, I guess that can be one motivation, but it's not the only motivation, right? Because if that was the only motivation, then after you graduate from a college, then there won't be any need for automated theorem proving anymore. Okay, so what would be the purpose of automated theorem proving? Well, I can give you another example to illustrate this. Um, is that okay if I raise the chair just a little bit? Okay. All right. So let me give you an example. Okay. I'll give you an algorithm. Okay. So new, there we go. And then we turn off line numbers. There we go. Okay. So let's just say that I have two variables, x and y. I want to find the maximum of those two and then store the maximum in a variable z. Are we good so far? And I want you guys to write that algorithm. So I go like, oh, okay, so it looks like this will work. Okay, if x is greater than or equal to y, then z gets the value of x, okay, because we're looking for the maximum. Otherwise, in this case, z gets the value of y. So it looks like this will solve the problem, right? It will find the maximum and then store the maximum in variable z. So now, if I say, hey, if this algorithm does not work, you're going to have to pay me 20 bucks. So how do you make sure that you don't pay me 20 bucks? How do you make sure that this algorithm is in fact correct? So it would be nice if we can do that, right? Because you can generate test cases. You can say, okay, what are the types of x, y, and z? They're all integers, okay? Then you can go like, okay, let's try it. Okay, let's say x is 3 and y is 2. So if x is 3, y is 2, 3 is greater than or equal to 2, and therefore z getting the value of 3 is the correct outcome. Okay. What if we flip it around and say that x is 2 and y is 3, and you can basically run the code and prove that, well, in that case, z gets the value of 3 also because this time y has the maximum and it works too. But how do you know for sure that it will work for every possible integer value? Well, you can generate all the possible test cases. Even with a 64-bit X and a 64-bit Y, there are only so many combinations of X and Y, right? So you can do it that way. You can exhaustively test this code to make sure that it works for every possible value of X and Y. But we are really looking at a huge test case, a huge number of test cases here, because X, assuming we're working with 64-bit integers, because that's kind of the normal thing these days. So X by itself has 2 to the power of 64 unique values, and then you have to multiply that to all the values that Y can also have, which is also 2 to the power of 64. So when you look at the product of these two, we are looking at 2 to the power of 128. Okay, so that means if you set up a double loop, okay, x goes from 0 to the largest unsigned 64-bit value, and then inside that outer loop, you also have a nested loop so that y, you'll do the same thing, going from 0 to the largest unsigned 64-bit integer. That double loop is going to take a long time to execute. Even with super fast computer these days, it will still take a long time to execute. Does that make sense? So this is not a really viable approach to say that, oh yeah, this algorithm is going to work in every possible case. So a better way to look at this is to say, oh, okay, we can prove it. So the way we prove, okay, I haven't talked about it in this class, but I can basically really quickly introduce the concept of pre and post conditions. The funny thing about pre and post condition is this is actually what CISP 300 is supposed to teach. Yes, I said CISP 300. Okay, so if you have a conditional statement, okay, so we'll look at the assignment statement first, okay. So let's just say that on line 37, okay, for no particular reason we start with line 37. So let's just say on line 37 we have a C statement that says x equals to 37. No, that's too lame. 61, okay. And also, let's just say that the precondition of line 37, for no particular reason that we need to care about in this class, has something to do with, oh, we know that w is greater than y. We know that y has to be less than w. Cannot be that w because that would be conflicting. Less than v, okay? And we also know that x is exactly 75. Don't ask me why, but that's basically what we were told, and we were able to prove everything up to the precondition of line 37. So now we go to line 37 itself, and then we ask, after line 37, what do we know? That's the post condition of line 37. So you go like, well, we're not changing w, we're not changing y, so the relationship between those two should be maintained. Okay. And we are not changing y, we are not changing v, so that should be maintained. But in this case, x would not be equal to 75 anymore. Now it would equal to 61 exactly. So that's basically the analysis of the precondition and the postcondition based on what statement is in between. Are we doing okay so far? More or less. Okay. So what if we have something a little bit more complicated than this? What if line 75 is x gets x plus 1? Okay. And for whatever strange reason, before line 75, immediately before line 75, we have the conclusion that, so in this case, I can make it a little bit simpler. For whatever strange reason, we just know that x is greater than w. Okay, that's the precondition. Okay, rather simple. So now we can now ask, what about the post condition? After line 75 executes, what do we know for sure? Given the precondition is what we know for sure before line 75 executes, immediately after line 75 executes, what will we know? You go like, well, since we just changed x, we wouldn't know anything about the relationship between x and w. Well, that would be incorrect because we can actually quote unquote apply the inverse function thing, and we can say, you know, I know what we just did to x. So let's go back to the previous value of x, which is x minus 1. So that was the previous value of x. Guess what? We knew that value was greater than w. So x minus 1 will still be greater than w because all we did on line 75 is to just add 1 to x. Is that okay? So we are deriving um, pre and post conditions. So now when you have conditional statements, it gets a little bit more hairy. So with conditional statements, okay, we'll just go ahead and use line just 91. Okay, so line 91 says, if some kind of condition C1, okay, and 92, goes like, we'll do some block statement here, okay, we'll say blah. And line 93 is the else, and then line 94 is more blah, okay, yada, yada. Okay, there we go. Okay. So now what do we do about this? Okay. Well, if we know what is pre 91, blah or pre 92 would be the same. So pre 92 is going to be the same as pre 91, but it also has a conjunction of C1. Okay, so we're gonna pause here and see if that makes sense to you or not. Does that make sense to you? Because I assuming C1 does not have any side effects. In other words, you're not trying to sneak in an assignment expression into C1. Assuming C1 has no side effect whatsoever, the values of all the variables have not changed. So that means whatever we know for sure is true before line 91 will still be true when we get to right before line 92. And as a result, but on top of that, we also know that C1 is true because otherwise we would not be going to the then branch, right? And I can say the same thing about pre 94, okay? So pre 94 is going to be pre 91, but this time we also have the conjunction with the negation of C1 because 94 or line 94 is the then branch of the conditional statement. We would only go there if and only if C1 is false. So that means right before yada executes, I don't even care what it is, we know for sure that whatever is in pre 91 that will still be true because we just evaluated a condition and already said that the C1 as a condition is has no side effect. So now we also know that C1 has to be false by the time we get to line 94 because that's the else branch. So by knowing the behavior of a conditional branch or conditional statement, we can now confirm all of these things, even though we have no idea what is C1 or what is exactly pre-91. But because this is a conditional statement, the two branches have to merge before the whole thing exits, right? So that means if I have a line 95 here, which is actually after the entire conditional statement, I can actually say something about pre-95 because pre 95, now I have no idea what blah is going to do. I have no idea what yada is going to do. Okay. But at least I know this is going to be post 92, whoops, 92, or post 94 because we have to come from either after the blah or after the yada. Okay. Now, I have no idea what blah is going to do, so I cannot derive post 92 without knowing exactly what blah is. For the same reason, I cannot derive what is post 94. So I'm just going to say, okay, whatever that thing turns out to be. But because by the time we get to line 95, it is after the entire conditional statement, it must have gone through one of the two branches. Now, which branch did it go through? I don't know. I don't even know what is C1, right? So that means, but I can still draw this conclusion of post 92 or post 94. Does that make sense? This is basically a really tedious way of using text to draw a flow chart. Is that okay? So you go like, well, how is this related to this class at all? Okay, so now we plug in our actual algorithm. Okay, so we go back, we look at our algorithm here, okay, and we just kind of stick a line 5 here. So now we perform exactly the same analysis. So in this case, we say pre1 is just true. The reason why we want to say pre1 is just true is I really have no idea how the variables are relating to each other. I have no assumption that x is greater than or equal to y or x is less than y. Okay, I just make zero assumption. So in other words, I'm looking for an expression that is true all the time. So what is an expression that is true all the time? True itself, right? Exactly. So by saying the precondition of alignment is true, I'm saying absolutely nothing. I'm simply saying I have no idea how the how the variables relate to each other, which is exactly right. Okay, because if I knew that x is greater than or equal to y, I don't need an algorithm to find the maximum. Okay, so with that in place, so now we go to line 2. What is the precondition of line 2? It is the precondition of line 1 using the structure that we found earlier and C1, but this time C1 is known. So basically C1 is just, oh, we just confirmed that x is greater than or equal to y. And then pre4 is going to be pre1 and it is not the case, which is, the other way to say that is x is less than y. Are we good so far? All right. So now we look at this and go like, well, we kind of know what pre1 is. It is just true. So true and whatever is just that whatever. Because true is the identity of conjunction. True and whatever is whatever. Are we good with that? Okay. So it's just a step of simplification in this case. So the other one is kind of the same thing, okay, except we have x is less than y instead. So now we just confirm that x is in fact less than y. Are we good so far? So now we look at the precondition and then we look at what is the post condition of line 2. In other words, right after line 2 executes, what are we going to know? Well, is it going to change the relationship between x and y? If you look at line 2, does that change x or y? Nope, it does not. So that means everything that we knew about x and y would still be true. However, everything that we knew about z would not be true anymore. Okay, but we now know after line 2 that z and x are actually the same because of the assignment statement. So that means post 2 is going to be x is greater than or equal to y, and guess what? Z and x, they must be the same because of the assignment statement on line 2. Are we good? All right. So now we do the same thing with post 4. Okay, so we say post 4 is the same as x is less than y because we did not change x nor y, but we did have an assignment statement. So by this time we know y, we know z is y. Is that okay? All right. So by using the structure that we saw earlier about how the two branches of a conditional statement has to merge, which means the post condition of the entire conditional statement is the or of the post condition of each branch. So now we can say, okay, we'll just kind of copy and paste the structure. And now we can say pre 5, okay? In other words, immediately before line 5 executes, whatever line 5 has, is the or between those two. So, I'm just gonna do the lazy thing, okay? And we go like, oh, not this one, because it's the post condition of line 2. Okay, well, I'll spout it out. It's post 2 or post 4. And now, but we also know what is post 2. Post 2 is this mess over here. And then post 4 is this mess over here. All right, so let's try to read this, entire thing. It says x is greater than or equal to y and z equals to x, or x is less than y and z equals to y. Is that kind of like a long way to say that, oh, okay, so I think you just want to say that z is the maximum of x and y. Is that okay? All right. So this is what I mean by proving an algorithm is correct using proofs, because this is a proof. Okay, it's a very step-by-step process. Okay, it can be very mechanical. It is extremely tedious if you, especially if you have loops, okay, or arrays, okay, involved. It can be very tedious, but nonetheless, it is really step by step. One step follows another step. We can establish a logical structure in order to analyze our algorithms. Is that okay? All right. So this is a really simple algorithm, right? It's just finding the maximum of two variables. Okay, no big deal. And there's no precondition to speak of in any way because we really do not need to know the relationship between x, y, or z prior to the execution of the algorithm. So pretty easy. So now the next question is, what if we are dealing with a sorting algorithm? Okay, in other words, with a sorting algorithm. Okay, so I'm going to go here. So we can say that before the whole thing, we can basically say a bracket 0 equals to k0 and a bracket 1 equals to k1 and so on, okay, until we get to the last element of the array. So we can say a bracket n minus 1 is k of n minus 1. Okay, I cannot do subscript here, but n minus 1 is supposed to be a subscript. So this way I can assign a specific value to the original content of a bracket 0. So this kind of brings us back to the whole discussion at the end of the discussion of bijection. Okay, because I was saying, okay, in order to qualify whether an algorithm is sorting an array or not, we're going to use a bunch of conditions. So in this case, let's just say the algorithm itself is 27 lines. Okay, so by the time we get to line 27, the post condition, so now we have to specify, okay, the logical expression to um, qualify uh, that array A is sorted in place. That whole expression is already discussed in this class when we talked about bijection, so I'm not going to repeat it here. But the bottom line is it is some kind of statement that can either be true or false. Are we good so far with that? Okay. So now the question is, attack, how do we prove that, if pre-1 is like this, post-27 is going to look like this? We do the same kind of analysis that we just did, but this time with loops, arrays, and so on and so forth. It's going to be tedious and long, but hopefully we can still do it mathematically. We can prove the correctness of the algorithm. Is that okay? All right. Are we making the association of, oh, okay, so I guess, one way to prove an algorithm is correct is to mathematically go through this whole process so that we can arrive to a post condition for an entire algorithm and make sure that that is what we want. Well, this is the only way to make sure that it works in all cases. You can always give it like test cases, right? You go like, okay, I'm going to give it a particular array and see if that works. It works for that array. Quicksort is recursive. So recursive algorithms actually they're easy in a certain way. So for a computer science person, like a professor at a 4-year university, it shouldn't take long. Yep. So, but why is this important? Can't we just give it some test cases and observe the output of the test cases and call it a day? What is the problem with that approach? Well, not exactly infinite, but it's large enough that we cannot cover all the possible cases, right? So that means, there are always this little gnawing feeling that you might have missed something, right? Okay, so that's not a good thing. All right, so now we look at this and go like, well, what is the whole idea of trying to prove a simple, stupid, sorting algorithm, using this much math? Does hmm? Check for bugs, right? But why is it important to check for bugs? Correct. But if your sorting algorithm is wrong, okay, maybe it will just report the wrong person as the gamer of the week. It's no big deal. You might have some gamers, canceling your game, but usually. Exactly. So what kind of algorithm is important enough that we go like, we really want to make sure this algorithm does what it's supposed to. hmm So there's this little thing, okay, I think you guys may not have remembered because you may be a little bit too young when it happened. Okay, it has a date here. Um, yeah, so this is OpenSSL, okay, which is at the backbone of using of HTTPS connections. Okay, so what is the significance of HTTPS versus HTTP connections? Yep. So it addresses two really important issues. One is encryption, the other one is um, auth- authentication. That's it. Okay. So there are two related things. They're not exactly the same thing. They can be using the same mechanism. One is called encryption. which is basically saying, okay, you are over at Starbucks, okay? There's open Wi-Fi, okay? It doesn't need anything to sign in, right? So if it doesn't take anything to sign in, there's no encryption, of anything going from your computer to the Wi-Fi router, right? So anyone, okay, the person sitting next to you can easily sniff all your packets and know exactly what zeros and ones get transmitted from your computer to the router and back. Okay. Then you go like, oh, that is not a good scenario. That means, when I'm doing online banking, the other person can find out, my password and how much money I have in the bank or how much debt we have in the bank and so on and so forth. That is a bad scenario. Well, that's why HTTPS is nice because HTTP itself is a plain text protocol, which means if somebody can sniff your HTTP traffic, they get to see your username, they get to see your password, and when the bank comes back with a reply, they get to see your balance. They get to see everything that you see. Okay, not a really good scenario. HTTPS, the S stands for the secure, okay, secured. So with that one, everything is end-to-end encrypted, which means there's a key exchange process, prior to the actual data exchange. Everything that you send to, say, Wells Fargo Bank is encrypted in a way that only Wells Fargo Bank, the server, can decrypt. Everything that they send back as a reply, only your computer can decrypt it. Okay, so that means the next person who's sitting next to you can go like, oh, I sniff all your traffic. I get all the zeros and ones, but it makes no sense to me because it's all gibberish to me. Yep. It is not. It's it's not simple like that, unfortunately, because in the case of the Heartbleed um, security hole, it has to do with the use of memory and the exposure of the memory window within the program itself. Okay, so but it also has to do with how the library, OpenSSL, is not responding to a incorrectly formatted request. So that instead of just dumping the request, it's like your request does not follow this format, chuck it. Okay, so instead of doing that, it actually replied to the request with the content, random location content of the memory of the server. Okay, so it is likely that 999 times out of 1,000, it will come back with some memory content that has no that is of no use to a hacker. That's entirely possible. But the 1,000th, probe may come back and say, "Oh, this is the encryption key for somebody else's communication." It can happen. Yes. Well, that's a whole different ball of wax. Okay, this one has to do with just securing a connection. An API key is a unique thing to identify I am developer so and so, or this particular program is associated with a particular paid account. So the API key is a whole different thing. And an API key in some way is more of an ID than it is a password or authentication means. So it's a little bit different in that case. Okay, so it led to a lot of problems. Okay, if you guys read this whole thing here, and a lot of this really has to do with a buffer overread problem, which means a incorrectly formatted request to the server will come back with a reply and go like, oh, okay, this is the content, or this is some of the content of my quote unquote buffer or dynamically allocated memory in this case. Any way you look at this, it is due to a programming flaw, okay, which can also be described as, oh, if this library was to function correctly, the output of this program has to meet these requirements, okay? If the input if the request does not meet these requirements, then the post condition is I am not replying. I'm dumping the request, I'm dumping the packet, I'm not going to come back with anything at all. But the program obviously did not do that. So, which means if we can somehow mathematically qualify the correct outcome of OpenSSL, that's one requirement. Two, and we can prove mathematically using the technique that we just talked about the actual outcome of the algorithm, we can at least three come to a conclusion whether the code is doing what it's supposed to do or not. Now, does this process help you debug the program? Probably not, okay? But it can at least tell you, oh, don't release this code. This is bad, okay? It is not meeting the requirement that you specified. Are we doing okay so far with that kind of argument? So this entire discussion up to this point is really just to show you the importance of automated theorem proving in the context of software engineering. Okay, so I can point you to the actual term here if you want to look more into it. It is called automated theorem proving. There we go, which has its own page on Wikipedia. Are we good so far? So this whole topic was of academic interest back in, I would say, the 70s and the 80s. Okay, so back in the 70s and 80s, it was of purely academic interest, which means nobody really connected this particular field to computer security. Why do you think it is now resurfacing as something that is, oh, this is really important, okay? Because we got security issues when we cannot do this. So why do you think it was only of academic importance back then, but now it actually has pragmatic applications? Hmm? Yes, exactly. Okay. So does that mean back in 1975, everybody who used a computer is really law abiding and really good citizens and all that stuff? Absolutely not. Okay. Programmers, computer scientists, and so on, they are the most morally gray people ever existed in the entire universe. They're not bad people, but they're also not good people. They just want to know what is possible and what is not possible. Okay. So their curiosity just kind of crossed the line. Sometimes it's like, I wonder if this is possible. And they would do something to prove whether it is possible or not. Sometimes it might trigger the meltdown of a nuclear plant in the process. So you go like, okay. So anyway, getting back to the main topic here. So So back then, there are bad people too. Okay, they want to infect your computer. They want your screen to show tech just hacked your computer. Ha ha ha. And then your floppy drive will be turning at the time, and then it goes like all your data is now erased. Ha ha ha. Again. Yes, go ahead. Hmm? The guy who created the dark web. What about? Yep, I guess so. I mean, only programmers can do that, by the way. Yep. Yep. And there's no way you can vibe code the dark web either. Yep. That takes a lot of actual expertise. So back in those days, there are people who want to hack your computer, just to show the message of, yep, I got you. Okay. And those programs, the malware, the malicious software, can spread too. Then you go like, but you don't have like massive networking. How do you spread a malicious program? You take the floppy disk out of a computer, you walk over to the next computer, you put the floppy disk into the next computer, clack, 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 do a bunch of command line stuff, and then you can infect the next computer. So how fast and how widely can you infect computers when that is the only way for you to spread a virus? It cannot be too fast. It cannot go too far either. Okay, because back in those days, the only way you can communicate digitally over any type of distance would be using your modem. But because modems are basically using your phone line, and back in those days, you know, anything that is not in Sacramento is a distance call, and it's expensive to make a distance call. So people do not make distance calls. Okay, hackers typically do not have a whole lot of money. Okay, they are not Elon Musk's. Hmm? Yep. Yep, but back in those days, we have bulletin board service, okay, which is kind of the digital version of CB radio. They can relay a message from one BBS to another BBS because they are still within a local call. So they would basically just use local call to another hop, local call to another hop, to local call to another hop, and so on. Okay, so the speed that a virus can spread is extremely low. Okay, and most hard drives back in those days only have 10 megabytes. You heard me right. Megabytes. Okay. And it's only about 5 to 10. So, in case of a quote unquote security breach, what are you breaching? Not a whole lot, because there's not a whole lot to begin with. Are you guys getting the idea of why computer security was not really that big of a deal back then? Hmm? 2010, the what drop? For Oh, that's more of a form of a DDoS. Okay, it's a distributed denial of service attack. That can cause a loss of service. Okay, but not necessarily, getting the data out of something. So fast forwarding, okay, from 75 to 2025, 50 years, right? So these days, everything is online. Okay, not only do we have everything online, we also have AI. We have agentic AI these days. Okay, what exactly is agentic AI? What do you know about agentic AI? Hmm? Agentic AI. Agentic, meaning it is using an agent of some kind in the context of AI. You guys don't know this? Yeah. Yeah, so you can literally use agentic AI. You can tell ChatGPT to sign in to the Canvas system we have here, go to a particular class, and do the homework for you. But you do have to supply your ID and your password to ChatGPT, and it can do the rest. I am not kidding you. Hmm? So use agentic AI to do homework in Canvas. I'm, I, there we go. So this can make pages. But and a professor actually figured out how to do this and did a demo, like a 5-minute demo of how to use, ChatGPT to do the homework. And you guys go like, well, I know how to do that. I mean, that's pretty easy. I sign into Canvas, I go to the homework assignment, I copy and paste, the question, put it into the prompt, copy and paste the answer back into the homework assignment, click submit. See, I know how to cheat too. No, we are talking about automating the whole process. Okay, all you have to do is to say, okay, do this for me. This is my ID, this is my password, do the whole thing for me. So, from that perspective, security becomes a big thing because we are basically disclosing, all this information, password and whatnot, on the internet to all the AI agents and whatnot. Okay, Um, what was the last time you get a paper statement from your bank or from the phone company or from your mobile service provider? Almost never anymore. Okay, everybody wants to go paperless because it is inexpensive, right? So that means we have all this data sitting on the internet, just waiting to be hacked. Okay, And that is why automated theorem proving is coming back because the importance is now going like, wow, okay, we really need to lock down certain types of software. I'm not talking about Windows, okay? Windows can crash all day long. It can give you the blue screen of death all day long, but it is usually not a security issue, okay? So we are talking about exactly what we were looking at before. We're looking at problems that are really at the core of digital communication, or at the core of how data is stored, or at the core of how databases manage, the interaction with outside agents. So with those critical components in modern day information system structure, we really kind of want to be able to use automated theorem and take an algorithm. Whoops, where is my mouse pad? Mouse pad, come on, come on. Oh, I moved it out of the screen. So we want to basically say, hey, computer, I need you to tell me with this algorithm, is the post condition exactly saying that Z is the maximum of X and Y? Except we are not dealing with simple algorithms like this. We're talking about things that can process networking protocols, packets, and so on and so forth. But still, we want to be able to, one, at least specify what the outcome is supposed to be, mathematically speaking, using quantified statements and whatnot, which we talk about a lot in this class already. And if possible, we also want to be able to use the computer to do the proving because it's really tedious. Okay, when you have a program or when you have a library that is like, say, let's just say it's a small one, okay, 50,000 lines of code, that's considered fairly small, okay, and you want to do it by hand with a person or with humans, forget it, it's too much. But if you use an automated system and use AI to do it, potentially you can do it. Now, this kind of AI is not GPT, LLM kind of AI. This is rigorous math, proving kind of AI. Yes. Mm-hmm. Mm-hmm. Yeah. Yep. Recipe or resume? Oh, recipe. Okay, got it. Yep. Well, we are automating everything. People are using AI to generate resume, and then employers are using AI to filter said resume, right? So it's resume, I mean, it's AI versus AI, just like in the comic, Mad magazine, they have spy versus spy. Okay, now we have basically AI versus AI, and that's why nobody gets hired. Every company is getting like a bazillion resume, and there's no way they can actually see who is applying and what is real and what is not real anymore. So I think at some point we're going to go back to face to face. I mean, can you spam face to face? Yes, but not at the scale of electronic spamming. In other words, if after you graduate from here, Sac State, UC Davis, or even UC Berkeley, you can drive down to the Silicon Valley, okay? And then you can just spend the whole day at the most expensive coffee shop next to the Google campus. And then you are just waiting for Google employees to get into the shop, and then you just go like, hey, this is my resume. I'm really good at programming and whatnot, okay? Yes, you can still spam, okay? But how much can you spam on a daily basis? Not a whole lot, right? Yeah, so I think things are going back to face, relatively soon. Thanks to AI, it really accelerates the whole thing back to in person. Hmm. Well, what will happen in that case is they are going to fingerprint. They will find out the fingerprint on the thumb drive, and they will find you. And then the Department of Homeland Security will come look at you. It's like, okay, so why are you doing this? What is on those hard drives? And then as it turns out, those hard drives were made in China, and it is not you. It is some manufacturer in China that built in malware to the hard drives. But DHS does not care. They think you did it. So now you're going to jail for no reason. Do you know how easy it is to do something like that? You can have a USB device, like a little dongle, for a keyboard, for a wireless keyboard, CD-ROM. Yep, you can make you can make your USB device look like as many devices as you want because a USB hub is essentially going like, oh, I'm just a hub. There are many, many devices behind me. So you can now say, oh, one of the devices behind me is a CD-ROM drive. Older versions of Windows and the ones that are not secured will go like, oh, CD-ROM, let me open it for you. Let me play this for you. And then whoop, there you go. Malware installed and trip every single alarm possible on this campus. Anyway, um, am I conveying the importance of automated theorem proving in the context of today's world? All right. So the question is, hey, does that mean that does this mean that I can just go, kind of go to some, Google executive and go like, I took tax class on, you know, discrete math and I know about propositional logic, so now I can help you guys to do theorem proving and make sure that everything is secure with your company. The answer is no, okay? Because your propositional logic is one of the simplest logic system, it is not directly useful for theorem proving to the point where you can secure and go like, oh, okay, we know this piece of software is doing what it is supposed to, but it is a starting point. Okay, so this is a good starting point. All right, so now we go back and take a look at where is it? So now we go back and take a look at propositional logic. Okay, so conventionally we have all of these derivations, and some of these are kind of useful. Okay, and they're at the same time it's like maybe, maybe not. Okay, let me give you an example of something that seems to be useful, but it is not exactly super useful. Okay, so I can give you a production here. So if I know P is true, I can say that implies P and P is true. Okay, is it valid? Sure, right? It is valid. So using the very same production, I can now say, hey, P and P being true implies, I think you guys are starting to understand what I mean by that, right? Okay, so it means this and this is also true. Yes? So I can repeat this approach a bazillion times but it is all meaningless. Okay, even though each step is valid, but the end result is like, yeah, but this is not really useful. Yes, and what do you mean by empty? These are Boolean expressions. There's nothing empty here. These are not sets. What? Empty is not a value. Okay. No, in this case, you have to know whatever you start off with on the left-hand side is true to begin with. We are basically saying, okay, if we know the left-hand side is already true, what can we deduce to be also true? Okay, but the whole point is I can keep doing this, and none of this is probably going to where I need the program to go. So that means, if I need the program to do any type of theorem proving, knowing which rule to apply when is kind of important. Does that make sense? Because how many statements like this can I make? If I just know that P is true, how many times can I go through this and still have quote unquote valid derivation that is useless? The answer is infinite. Exactly. Okay. So what about the one statement that I really want to arrive? Okay. Well, let's call that the needle. Okay. So the needle is the statement that I need to prove to be true. Okay. So if I were to ask you to look for a needle in a haystack that is infinitely large, what do you think is the problem? Hmm? And do you think if I give you a big magnet, do you think you can complete the task? Can you? No. No, you cannot complete the task, okay? Because you cannot even differentiate between the needle is somewhere in the haystack, I just have not found it yet, versus the needle is not even in the haystack. If you cannot distinguish between those two, then there's no hope to actually take on the task because you cannot just go like, oh, okay, tack, you just tricked me. The needle is not even in the haystack. Okay, because in that case at least you come back and say, okay, I'm done. Okay, I have concluded that the needle is not even in the haystack. But if you don't, if the haystack itself is infinitely large, then you are really just relying on luck to go like, maybe I can find the needle, if assuming the needle does exist. Okay, so that is the problem of propositional logic, is if you know the needle is in the haystack, then maybe you get lucky and find a path leading to the needle. Okay, which is the case in all of your homework assignments. Okay, in your math homework assignments, the professor will always give you something that is known to be true, and your task is to find the path to the needle. But we know the needle is in the haystack. Okay, but in this case, we don't even know, okay, whether the needle is in a haystack. In other words, I give you some really bogus algorithm. I don't even know whether it is provable or not that the algorithm will do what we need it to do. So that means the approach of using conventional propositional logic is not going to be very helpful. Is that okay? And on top of that, okay, if you take this class from anyone else, they will ask you to remember all of these things, give you some examples or give you some exercises where, okay, these statements are known to be true and we want to derive that statement over there which is known to be true to begin with. So you're really just looking for a path to something that is known to be true. Okay, which means you know the needle is in a haystack. It's just a matter of, okay, how do I find it? Okay, what is the quickest way to get to the needle? That is not realistic. Okay, so in this class I'm going to start with this. Okay, and we won't have enough time to really dig into the full mechanical aspect of propositional logic, so that's something that we're going to do next Wednesday because Monday is our exam one. Okay, so next Wednesday we'll go back to the notes and then we'll dissect, we'll basically figure out what are the mechanical components of a propositional logic system, and how do we use it in a way so that the haystack has a finite size. Okay, because when the haystack has a finite size, and we can actually know that, oh, tack, you just tricked me, that needle does not even exist in the haystack, because there's only so much stuff you have to go through. You can go through every single one of those, the needle is not there, you can come to a conclusion. So that's the direction of this class at this point. Okay, we are going to deal with propositional logic, but in a way that will give us some ideas of how to prove theorems, but in a pragmatic way. Yes. Yep. Back in the Greek days, this is what they use it for. And that's why they all have names, because in a debate back in those days, you use logic to try to convince the other side that what you say is the truth. So you have to name all the steps that you're taking. And then you go like, well, based on this and that, use the names of the rules, we can now derive that this is true. So that's why every single one of those derivation has a name because this is used in a logical debate back in those days. All right, so I'm just gonna let you guys out a little bit early today. Okay, next Monday is our exam one, and then next Wednesday we'll come back and talk about this. So reading ahead of time is going to be quite useful. This is not an easy module to read. Okay, if you think the previous ones were bad, I'm not gonna say anything. If you think so, try to spend some time on this one, okay? Because this one is a little bit difficult to read, but it is also, I think, in some way, more useful or more pragmatic compared to some of the other ones. All right. So have a nice weekend. I'll see you all on Monday, and we'll try to get into the classroom earlier next Monday, just so that you guys have time to set up and whatnot. All right. So I'm gonna stop the recorder.